On the first day of July, 2025, a robotic telescope in the high desert of Chile captures something unusual. The telescope is part of a system called Atlas Asteroid Terrestrial Impact Last Alert System, designed to scan the sky methodically, night after night, searching for objects that move against the background of stars. Most nights, it finds asteroids, small, dark, unremarkable. But on this night, in the dense star fields near the constellation Sagittarius, where the Milky Way's central bulge blazes with ancient light, the telescope records a point of brightness that should not be there. The object is faint, magnitude 18, invisible to any human eye without significant magnification. It sits approximately 410 million miles from the Sun, drifting just beyond the orbit of Jupiter, and it moves, not the slow drift of a distant asteroid, but something faster, something with purpose, though purpose is the wrong word. Physics is the better word. Momentum, velocity inherited from somewhere else entirely. The discovery is logged. A temporary designation is assigned A11PL3Z. Within hours, other observatories begin to look, amateur astronomers in backyard observatories, professional instruments atop mountains in Hawaii and Arizona. Pre-discovery images are found, observations from June 28th, June 21st, even June 5th frames where the object had been present all along, unnoticed because it was passing directly in front of the galactic center, camouflaged against millions of stars packed into a visual space smaller than a full moon. The data accumulates, positions are measured, trajectories are calculated, and within days, the realization settles over the astronomical community like a slow exhale. This object is not from here. Its orbit does not close. It follows a hyperbolic path, a shape that implies escape velocity, that implies origin beyond the Sun's gravitational dominion. When astronomers trace the trajectory backward through time, accounting for the Sun's pull and the gentle perturbations of the outer planets, the path does not curve back toward the Oort cloud or the Kuiper belt. It comes from interstellar space, from the region between stars, from elsewhere. It is only the third such object ever confirmed. The first, Oumuamua, arrived in 2017 and departed before most telescopes could properly study it. The second, Borisov, appeared in 2019, a comet, clearly active, visibly shedding gas and dust in ways that matched expectations. But this one, this third visitor, already seems different. The object is named 3I Atlas. The I denotes interstellar. The 3 marks it as the third of its kind. The Atlas honours the survey that found it. A simple designation for something that has been moving through the galaxy for timescales we can barely comprehend. At the moment of discovery, 3I Atlas is travelling at approximately 61 kilometers per second relative to the Sun. To put this in context, if you could somehow stand still in space, anchored to the Sun's reference frame, and watch this object pass, it would cross the distance from Earth to the Moon in less than 2 hours. It would traverse the space between Earth and the Sun, one astronomical unit, the fundamental yardstick of our solar system, in roughly 29 days. This speed is extraordinary. The previous interstellar visitors moved at 26 and 32 kilometers per second upon entering the solar system. 3I Atlas is moving nearly twice as fast as Oumuamua. This suggests different origins, different ejection mechanics, different histories written in velocity alone. The sky is dark where the comet moves. It approaches from the direction of Sagittarius, from the galactic plane, from the direction where our galaxy's centre lies hidden behind vast clouds of dust and gas, if one could trace its path backward through the Milky Way. Accounting for 10 million years of galactic rotation and stellar encounters, one might find that it passed within a few light years of 25 known stars. But which star ejected it? Which planetary system gave birth to this frozen traveller? The answer is lost time. The comet has been wandering too long. The galaxy has turned too many times. Perhaps it formed in a solar system much like ours. Perhaps a close encounter with a gas giant, a Jupiter or Saturn of another star, flung it outward with enough velocity to escape. Perhaps its parent star died, shedding mass and loosening the gravitational bonds that held its outer comets in orbit. Perhaps something else, something we have not yet imagined, set it free. What is certain is this: for millions of years, possibly billions, 3I Atlas has been adrift in the cold between stars, travelling through regions where the temperature hovers just a few degrees above absolute zero, where the density of matter is so low that a cubic metre of space might contain only a single atom. It has been falling through the galaxy's gravitational potential, influenced by the collective mass of billions of stars, by the dark matter halo that enfolds the Milky Way, by forces so diffuse and patient that they reshape trajectories over eons. And now, by chance, by the simple geometry of intersecting paths in three-dimensional space, it has entered our solar system, not aimed, not guided, simply arriving, the way a leaf might drift into a quiet eddy of a stream, carried by currents too vast to attribute to intention. The telescopes watch, the data flows in, and already, even in these first nights of observation, the astronomers notice something unusual about the way this visitor glows. The work of tracing an orbit is mathematical and patient. It involves measuring positions against the backdrop of stars, right ascension and declination, the celestial equivalents of longitude and latitude, and recording those measurements with timestamps precise to fractions of a second. Each observation is a point in space and time. Each point constrains the possible paths the object might follow. For objects that belong to the solar system, this process converges quickly toward elliptical orbits. The mathematics of bound trajectories is well understood. An asteroid circling the Sun follows Kepler's laws with predictable regularity. Its orbital element's semi-major axis, eccentricity, inclination can be determined from a handful of good observations spread across a few weeks. But 3I Atlas does not cooperate with these expectations. The orbital eccentricity is the first parameter to diverge from normalcy. For circular orbits, eccentricity equals 0. For elliptical orbits like Earth's, eccentricity is a small positive number less than 1. But hyperbolic trajectories, paths followed by objects with enough velocity to escape the Sun's gravity entirely, have eccentricities greater than 1. The eccentricity of 3I Atlas is calculated at 6.141, plus or minus 0.002. This is extreme. This is a trajectory so open, so barely curved by the Sun's gravity, that it appears nearly straight when plotted on a solar system diagram. The comet is not visiting. It is passing through. It will never return. Astronomers input the observations into orbital calculation software. Programs with names like Horizons and SPICE ingest the data and produce ephemeridus tables predicting where the object will be at any given future time. The predictions show 3I Atlas moving inward, falling toward the Sun along a path tilted at only a few degrees relative to the ecliptic plane, the flat disk where the planets orbit. This alignment is curious. Most objects arriving from interstellar space would approach from random angles, uncorrelated with the solar system's architecture. But 3I Atlas moves almost within the same plane as Earth, Mars, Jupiter. It travels retrograde opposite to the direction of planetary motion, but it remains in the disk, as if it is following rules it should not know. The trajectory brings it close to Mars, not dangerously close, not in the sense of collision, but close enough that spacecraft orbiting the red planet might be able to observe it, close enough that the geometry becomes interesting. On October 3rd, 2025, 3I Atlas will pass within approximately 30 million kilometers of Mars. This is roughly 20% of the distance between Earth and the Sun. In cosmic terms, a whisper. The Mars Reconnaissance Orbiter, equipped with a high-resolution camera called HiRISE, could potentially image the comet if timing and brightness cooperate. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will also attempt observations, turning instruments designed to study Martian geology and atmosphere toward this visitor from between the stars. But before Mars, before perihelion, before any close approach, there is the matter of what the comet is doing now. In late June and early July, when 3C Atlas is still beyond Jupiter's orbit, when it remains more than 4 astronomical units from the Sun, observers notice a faint glow surrounding the nucleus, a coma, a nebulous envelope of material that makes the object appear fuzzy rather than point-like in images. This should not be happening. Comets brighten as they approach the Sun because solar radiation heats their surfaces, causing volatile ices, primarily water, to sublimate directly from solid to gas. This outgassing carries dust particles into space, forming the coma and eventually the tail. But this process requires a certain threshold of solar heating. Most comets do not become visibly active until they cross inside Jupiter's orbit. Many wait until they are significantly closer. 3I Atlas is glowing while still in the outer solar system, in a region where sunlight is weak and temperatures remain far below the sublimation point of water ice. Spectroscopic observations begin. Instruments split the comet's light into constituent wavelengths, searching for the characteristic signatures of specific molecules. On Earth, telescopes equipped with spectrographs point toward the visitor. In space, the James Webb Space Telescope, humanity's most powerful infrared observatory, turns its gaze toward 3I Atlas. The data returns, and the data is strange. The coma is dominated not by water vapor, but by carbon dioxide, dry ice. The ratio of carbon dioxide to water is among the highest ever measured in any comet, solar system or otherwise. Carbon dioxide sublimates at much lower temperatures than water at the distance where 3I Atlas currently travels. Dry ice can vaporize while water remains locked in solid form. This explains the early activity, but it raises other questions. Why would a comet be so rich in carbon dioxide relative to water? What does this say about where it formed, about the temperature and chemistry of its birth environment? Additional molecules are detected: carbon monoxide, carbonyl sulfide, small amounts of water vapor and water ice. The spectral lines appear and are measured and catalogued. There is also cyanide gas, hydrogen cyanide, molecular cousin to the poisons of Earth, and something unexpected atomic nickel vapor, sublimating from the comet's surface in concentrations similar to those seen in solar system comets. The reddish colour of the coma suggests the presence of Tholin's complex organic molecules formed when simpler compounds are irradiated by cosmic rays and ultraviolet light over long periods. Tholins are common on the surfaces of outer solar system objects. They are the reason Pluto appears tan and reddish-brown. They are the patina of deep time and radiation exposure. If 3I Atlas has been drifting through interstellar space for millions or billions of years, its surface has been bathed in galactic cosmic rays continuously. The reddish hue may be a kind of fossil record, a chemical signature of age and exposure written in colour. Hubble Space Telescope images from July 21st show additional detail. The coma is teardrop-shaped, with a faint dust structure extending in the direction of the Sun, an anti-tail pointing sunward rather than streaming away. This geometry is unusual but not impossible. It likely results from larger dust particles being released from the nucleus and following slightly different trajectories than the gas. The nucleus itself remains difficult to measure. It is small and surrounded by the glowing coma. Initial estimates suggest a diameter between 440 meters and 5.6 kilometers. This wide range reflects the difficulty of distinguishing the solid body from the material it sheds. Throughout July and August, observations accumulate, positional measurements are refined, the trajectory is known with increasing precision, and a small group of researchers begins to notice something else, something about the way the comet moves, or rather, about the way it does not move. Comets that outgas experience a recoil force. As gas jets away from the sun-heated surface, momentum is conserved. The comet is pushed in the opposite direction. like a slow-motion rocket engine. This effect is called non-gravitational acceleration, and it can be measured by comparing the comet's actual position over time with the position predicted by gravity alone. For 3I Atlas, observations span from May 15th through September 23rd, compiled from 4,022 measurements made by 227 observatories around the world. The data is extraordinarily precise. The deviations from a purely gravitational trajectory are analysed. The result is surprising. The non-gravitational acceleration is effectively zero, less than 15 meters per day squared, smaller than the measurement uncertainty for most comets. This makes no sense. Webb telescope data shows that 3I Atlas is losing mass at a rate of approximately 150 kilograms per second, with gas streaming away at 440 meters per second. This outgassing should produce measurable thrust, but the comet's path does not deviate. There is only one explanation that fits the observations: the comet is far more massive than initial estimates suggested. So massive that the rocket effect of outgassing is negligible. So massive that 150 kilograms per second of ejected material cannot measurably alter its trajectory. The calculations are performed. The minimum mass, given the observed outgassing and the absence of measurable acceleration, is 33 billion tons. At typical comet density, this implies a nucleus diameter of at least 5 kilometers, 5,000 meters, larger than the upper end of the range estimated from Hubble images. If this is correct, 3I Atlas is not merely unusual, it is anomalous. It is 3 to 5 orders of magnitude more massive than the previous interstellar objects. It is a statistical outlier so extreme that its very existence poses questions about the population of objects drifting between stars. The mathematics say one thing, the observations whisper another, and the comet continues inward, indifferent to the calculations performed in its name, moving according to laws older than speculation. Velocity is a kind of memory. An object's speed and direction encode the history of every gravitational encounter, every force that has acted upon it since its formation. For 3I Atlas, the velocity is extraordinary, a testament to origins we can only infer: 58 kilometers per second. This is the comet's speed relative to the Sun when it enters the solar system, measured at such great distance that the Sun's gravity has not yet substantially altered its motion. In astronomical terminology, this is called the hyperbolic excess velocity, the speed an object would retain if it could somehow escape the Sun's gravitational influence and return to interstellar space. To travel at 58 kilometers per second is to cross a distance equal to Earth's diameter in less than 4 minutes. It is to move so fast that the Sun's immense gravity can only bend the trajectory slightly, curving it into a shallow arc before releasing it back into the dark. The previous interstellar visitors moved more slowly. Oumuamua entered at 26 kilometers per second, Borisov at 32. These speeds were already remarkable, far faster than any object bound to the Sun, faster than any asteroid or comet in a closed orbit. But 3I Atlas moves at nearly double Oumuamua's velocity. It carries twice the kinetic energy per unit mass. It has been accelerated by different forces, by different gravitational histories. What imparts such velocity? One possibility is a close encounter with a massive planet in its birth system. Imagine a comet in a distant orbit around another star, moving slowly through the cold outer regions where such objects form. Now imagine a gas giant, a world with the mass of Jupiter or Saturn, whose own orbit has migrated inward over millions of years, disrupting the peaceful trajectories of smaller bodies, a close pass, a gravitational slingshot. The comet is flung outward with enough speed to escape the star entirely, cast into interstellar space like a stone from a celestial sling. This mechanism is well understood. Our own solar system likely ejects comets this way, though we cannot observe them once they depart. Every gravitational interaction between Jupiter and a passing comet has the potential to add or subtract orbital energy. Some comets fall inward toward the Sun, others are accelerated outward, beyond Neptune, beyond the Kuiper belt, beyond the point where the sun's gravity can hold them. But to reach 58 kilometers per second requires either a very close encounter or multiple interactions. The mathematics of gravitational assist are strict. Velocity changes are limited by the mass and speed of the planet doing the flinging. To achieve the speed observed for 3I Atlas might require ejection from a system with particularly massive planets, or ejection during a period of dynamical instability when multiple giant worlds scatter objects in chaotic ways. Another possibility involves stellar death. When low-mass stars exhaust their nuclear fuel, they expand into red giants, shedding outer layers and losing a significant fraction of their total mass. As the star's mass decreases, its gravitational hold on distant objects weakens. Comets in wide orbits may find themselves suddenly unbound. Their orbital energy unchanged, but the escape velocity now lower than their current speed. They drift away, not flung but simply released, like balloons let go by an inattentive hand. If 3I Atlas formed around a star that later became a red giant, it could have been set adrift in this gentle manner. The velocity would then reflect not violent ejection, but patient loss of binding energy over millions of years. A third scenario involves stellar flybys. The Sun moves through the galaxy at approximately 220 kilometers per second, relative to the local standard of rest. Other stars move at similar speeds, but in different directions. Occasionally, stars pass near one another not close enough to collide, but close enough that their gravitational fields perturb the outer regions of each other's planetary systems. A passing star could disturb the Oort cloud of another star, sending comets inward toward the central star or outward into interstellar space. If 3I Atlas was perturbed by such a flyby, its velocity might reflect the relative motion between its parent star and the interloping star. High relative velocities between stars would produce high-velocity ejections. The uncertainty is irreducible. We cannot trace the comet's path backward with sufficient precision to identify its origin. 10 million years of travel through the galaxy erases the trail. Stars move. The galaxy rotates. Gravitational encounters with molecular clouds and stellar clusters alter trajectories incrementally. The comet has passed through regions of varying density, felt the pull of structures too diffuse to see but massive enough to bend paths over millennia. What can be said with confidence is this: 3I Atlas has been travelling for a very long time. If it originated from the Milky Way's thick disk, a population of older stars above and below the galactic plane, it could be 7 billion years old or more. Older than the Sun, older than Earth, older than any rock we have touched or studied. A frozen artifact from the galaxy's early history, preserved in the cold of interstellar space, carrying chemistry and isotopic ratios that might reflect conditions in the disk when it was younger, when the abundance of heavy elements was lower, when star formation rates were different. Even if it is younger, even if it formed only a few billion years ago in the thin disk where the Sun resides, it has still traversed distances incomprehensible in human terms. Light years. Tens of light years, perhaps hundreds, drifting at 58 kilometers per second through a medium where the average density is 1 atom per cubic centimeter, where starlight is so faint that navigation by constellations would be impossible, where the only illumination comes from the collective glow of the galaxy itself. The interstellar medium is not empty. There are atoms of hydrogen, helium, traces of heavier elements. There are dust grains, microscopic particles of silicate and carbon. There is radiation, cosmic rays, photons from distant stars, the faint microwave background left over from the Big Bang. All of these interact with a passing comet, slowly, incrementally. Over millions of years, cosmic rays strike the comet's surface, breaking molecular bonds, creating new compounds, darkening the ice. Dust grains impact at relative velocities that can reach tens of kilometers per second. Each collision a microscopic explosion that vaporizes a tiny amount of material. The comet erodes. Its surface is weathered not by wind or water, but by the slow violence of interstellar space. And yet, despite this erosion, Despite eons of exposure, enough ice remains that when 3I Atlas finally enters a new solar system, when it finally feels the warmth of a star again after unimaginable cold, it can still sublimate, it can still glow, it can still betray its presence to the telescopes of a world it has never seen. As 3I Atlas falls inward toward the Sun through July and August, its speed increases. Gravitational potential energy converts to kinetic energy. The fundamental conservation laws of physics play out on a scale both intimate and vast. By the time it reaches perihelion in late October, the comet will be travelling at approximately 68 kilometers per second relative to the Sun. Faster than Discovery, faster than any human-made object has ever moved. And then, after perihelion, the process reverses. The comet climbs back out of the Sun's gravity well. Kinetic energy converts back to potential energy. The velocity decreases, asymptotically approaching the original 58 kilometers per second as the distance increases, but it will never stop. It will never fall back. The trajectory is open. The speed is too great. 3I Atlas will pass through the solar system once, and only once, in all the billions of years of cosmic history. The velocity guarantees departure. The velocity is the signature of elsewhere, written in meters per second, preserved across light years, delivered to our instruments with indifferent precision. There is a distance from the Sun where comets are supposed to remain inert, a boundary, not sharp but statistical, beyond which solar radiation is too weak to sublimate water ice in quantities sufficient to produce visible activity. This boundary lies somewhere around 5 astronomical units, roughly the orbit of Jupiter, though it varies depending on the composition and surface properties of individual comets. Most comets discovered beyond this distance appear as faint, star-like points. They reflect sunlight from their dark, frozen surfaces but produce no coma, no tail, no indication of the volatile ices locked within. They wait. They fall inward. Only when they cross into the inner solar system, when the Sun's warmth grows strong enough, do they begin to transform. 3 Atlas does not wait. When discovered on July 1st, the comet is 4.51 astronomical units from the Sun. This is farther than the average distance of Jupiter. At this distance, sunlight is diminished to roughly 4% of its intensity at Earth. The temperature of a dark, airless surface would be approximately 140 Kelvin minus 133 degrees Celsius, cold enough that water ice remains stable for billions of years, cold enough that most volatile activity should be absent, and yet the comet glows. Pre-discovery images from late June show the same phenomenon. On June 21st, at an even greater distance, a faint coma is already visible. The Zwicky Transient Facility captures it. The Atlas Survey telescopes record it. The object is not star-like but diffuse, surrounded by a halo of material that scatters sunlight. This early activity is the first clear indication that 3I Atlas is unusual in composition, not merely in trajectory. Water ice sublimates at temperatures around 150 to 200 Kelvin under solar system conditions warmer than the surface temperature at Jupiter's distance. But carbon dioxide ice, dry ice, sublimates at much lower temperatures. At pressures near vacuum, carbon dioxide transitions directly from solid to gas at around 150 Kelvin, and even this threshold is approximate. A comet rich in carbon dioxide can begin outgassing farther from the Sun than a water-rich comet, responding to solar heating that would leave water ice dormant. When the James Webb Space Telescope observes 3I Atlas in early August, the spectroscopic data confirms this hypothesis. The coma is dominated by carbon dioxide molecules. The ratio of CO2 to H2O is extraordinarily high, among the highest ever measured for any comet, whether from our solar system or interstellar. This raises questions about formation conditions. In protoplanetary disks, the rotating clouds of gas and dust that surround young stars and eventually condense into planets, the temperature varies with distance from the central star. Close in, near the star, Temperatures are high enough to vaporize even refractory materials like silicates and metals. Farther out, water ice can condense. Farther still, carbon dioxide ice becomes stable. Beyond that, carbon monoxide and nitrogen ices form. Each volatile has its own frost line, the distance from the star where temperatures drop low enough for that particular substance to freeze. A comet rich in carbon dioxide but relatively poor in water, likely formed beyond the water frost line but within or near the carbon dioxide frost line. This suggests formation in the cold outer regions of its parent planetary system, perhaps 10 or 20 astronomical units from the parent star, perhaps farther. For comparison, in our solar system, comets from the Kuiper belt formed at distances of 30 to 50 astronomical units from the Sun. Oort cloud comets may have formed closer in and been scattered outward, but they still condensed from material that reflected the Sun's early protoplanetary disk. Most solar system comets have water as their dominant volatile, with carbon dioxide present but secondary. 3I Atlas inverts this ratio. Its chemistry suggests a birth environment where carbon dioxide was more abundant than water, or where temperatures and pressures during formation favoured the incorporation of CO2 over H2O. This could indicate a parent star with different luminosity than the Sun, or a protoplanetary disk with unusual chemical composition, perhaps lower metallicity, perhaps different ratios of carbon to oxygen. If the comet originated from the galaxy's thick disk, the parent star might have formed when the Milky Way was younger, when the abundance of elements heavier than hydrogen and helium was lower. Stars with lower metallicity have protoplanetary disks with different chemistries. The building blocks are subtly altered. The ices that condense reflect these differences. Alternatively, the carbon dioxide dominance might be a surface effect. Billions of years of exposure to cosmic rays and ultraviolet photons in interstellar space could have preferentially eroded water ice, which is more reactive and more easily photodissociated than carbon dioxide. The comet's surface layers might be enriched in CO2 simply because the water has been slowly destroyed and lost over geological time. This is a quiet mystery, an uncertainty that observations cannot yet resolve. What is observable is the behaviour of the coma as the comet continues inward. Through July and August, Hubble images show the coma expanding. On June 21st, before discovery, the diameter is approximately 13,000 kilometres. By July 2nd, it has grown to 18,760 kilometres. This is larger than Earth, larger than any terrestrial planet. A cloud of gas and dust particles expanding into space, carried outward by the pressure of sublimating ice and the faint push of solar radiation. Within the coma, dust grains of different sizes move at different speeds. Small particles 1 micrometer in radius are ejected from the nucleus at approximately 22 meters per second. Larger grains 100 micrometers across move more slowly, at about 2 meters per second. The size distribution and velocity distribution of these particles tells a story about the forces at work. Gas drag pushing small particles faster, gravity and cohesion holding larger particles back, radiation pressure sorting particles by size. The coma has a reddish colour. Spectroscopic measurements place it in the same colour range as D-type asteroids and other carbon-rich bodies in the outer solar system. The redness likely comes from Tholin's complex organic molecules produced when simpler compounds like methane, ethane, and nitrogen are exposed to radiation over long periods. Tholins are not alive, but they are organic in the chemical sense they contain carbon-hydrogen bonds. They form naturally in environments where organic molecules and radiation coexist. They have been found on Titan's surface, in the atmospheres of Pluto and Triton, on the surfaces of Kuiper belt objects. They are the colour of deep time, the hue of radiation-processed carbon. If 3I Atlas has been drifting through the galaxy for billions of years, its surface has been irradiated continuously by cosmic rays, high-energy protons and atomic nuclei, accelerated by supernovae and other violent events. This radiation breaks chemical bonds, creates free radicals, drives reactions that would not occur in the absence of energy input. Over time, Simple ices are transformed into more complex molecules. The surface darkens. Reddish-brown compounds accumulate. The early glow of 3I Atlas, then, is not merely an anomaly. It is a clue. It suggests composition, history, age. It speaks of formation far from a star, of chemistry enriched in carbon dioxide, of exposure to the interstellar medium across timescales that dwarf human civilization. And it poses a gentle irony that an object from elsewhere should announce its arrival not by silence, not by darkness, but by shining earlier than expected, by glowing in a region of space where most of its solar system cousins would remain invisible. That the very strangeness of its chemistry makes it easier to detect, to study, to wonder about. The telescopes continue to watch. The coma continues to grow, and the comet falls inward, toward warmth it has not felt in billions of years, carrying ice that remembers a star whose name we will never know. Chemistry is a form of archaeology when the subjects are billions of years old. Each molecule detected in the coma of 3I Atlas carries information about conditions at the comet's birth, about the processes that have altered it since, about the nature of matter in regions of the galaxy we can never visit. The James Webb Space Telescope observes 3I Atlas on August 6, 2025. Webb is humanity's most sensitive infrared observatory, positioned at a gravitationally stable point in space called L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. Its instruments can detect the faint infrared glow of molecules warmed by sunlight or by their own internal vibrations. The spectrograph records wavelengths. Each molecule absorbs and emits light at characteristic frequencies determined by its quantum mechanical structure. Carbon dioxide has specific absorption bands in the infrared. Water vapor has others: carbon monoxide, methane, ammonia. Each leaves a unique fingerprint. The data from 3I Atlas shows carbon dioxide as the dominant volatile. The spectral lines are strong, clear, unmistakable. Water is present but secondary. The ratio is inverted compared to most comets, where a typical solar system comet might have 10 or 20 water molecules for every carbon dioxide molecule. 3I Atlas has roughly equal amounts, or even more carbon dioxide than water. This is rare. Not unprecedented, there are a handful of solar system comets with elevated CO2, but unusual enough to demand explanation. Also present carbon monoxide. This molecule is even more volatile than carbon dioxide, sublimating at temperatures below 100 Kelvin. Its presence suggests that some of the comet's ice has been cold enough, for long enough, to retain even the most fragile volatiles. Or perhaps the carbon monoxide is being produced by the breakdown of more complex molecules, organic compounds decomposing under solar radiation. Carbonyl sulfide appears in the spectrum as well. This molecule, with the chemical formula OCS, is less common. It contains sulfur, an element present in trace amounts in most comets but rarely abundant. Its detection adds another layer to the chemical portrait. This is not merely a ball of water ice with some carbon dioxide mixed in, but a complex aggregate of ices with sulfur-bearing compounds embedded in the matrix. Cyanide is detected by ground-based telescopes. Hydrogen cyanide, HCN, a molecule familiar from chemistry textbooks and detective novels. Toxic to humans but common in space. Comets often produce cyanide as they outguess. It forms from the breakdown of more complex organic molecules or sublimates directly from ice, where it has been frozen since the comet's formation. And then there is nickel, atomic nickel vapor, not molecular, not bound to other elements, but individual nickel atoms in gaseous form. This is unexpected. Nickel is a metal with a boiling point above 3000 Kelvin. To find it vaporizing from a comet's surface, even a sun-warmed surface, suggests unusual chemistry or unusual heating. Recent studies of solar system comets have detected nickel and iron atoms in their comae, a discovery that challenged assumptions about cometary composition. The leading hypothesis is that these metals are bound in volatile compounds organometallic molecules that sublimate at lower temperatures than pure metals. When these compounds enter the coma and are exposed to ultraviolet sunlight, they photodissociate, releasing free metal atoms. The detection of nickel in 3I Atlas suggests this comet shares this characteristic with its solar system cousins. The chemistry of comet formation, wherever it occurs, produces similar outcomes. Metal-bearing molecules form in protoplanetary disks around many stars. The physics is universal, even if the abundances vary. But the carbon dioxide dominance remains anomalous. One possible explanation involves the location of formation. If 3I Atlas condensed in a region of its parent protoplanetary disk where carbon dioxide ice was more abundant than water ice, it would naturally incorporate more CO2. This could occur if the disk was particularly cold, or if the carbon-to-oxygen ratio in the gas was different from the solar ratio. Stars with different metallicities, different abundances of elements heavier than hydrogen and helium, have protoplanetary disks with different chemistries. A star with lower metallicity might produce a disk where carbon and oxygen are present in different proportions. If carbon is relatively more abundant, or if oxygen is locked up in silicate minerals rather than available to form water, the resulting comets would be carbon dioxide rich. Another possibility is selective processing during the comet's long journey through interstellar space. Water ice is more susceptible to photodissociation by ultraviolet light than carbon dioxide ice. Over millions or billions of years, starlight and cosmic rays could preferentially destroy water molecules on the comet's surface, leaving carbon dioxide behind. The surface layers would become enriched in CO2 while deeper ice, shielded from radiation, might retain a more balanced composition. This scenario is testable, in principle. If the carbon dioxide dominance is only a surface effect, then as 3I Atlas approaches the Sun and sublimates deeper layers of ice, the chemical composition might shift. More water might appear, the CO2-H2O ratio might decrease. Observers are watching for this change. As of September, the ratio remains high. The carbon dioxide continues to dominate. If there is a water-rich interior, it has not yet been exposed. The organic molecules, the tholins that give the comet its reddish colour, add another dimension. Tholins are not a single compound, but a class of compounds. A mixture of carbon, hydrogen, nitrogen, oxygen structures, ranging from simple polymers to complex macromolecules. They form when simpler molecules are irradiated. They are the end product of radiation chemistry in cold environments. On 3I Atlas, the tholins likely formed during the comet's long drift through interstellar space. Cosmic rays struck the surface. High-energy particles broke chemical bonds. Free radicals formed and recombined. Over time, the simple ices methane, ethane, ammonia were transformed into larger, more stable molecules. The surface darkened, the reflectivity decreased, the comet became redder. This is a process that takes time. Not thousands of years, but millions, perhaps billions. The reddish colour of 3I Atlas is a kind of timestamp, a marker of age and exposure. The deeper the red, the longer the irradiation, the darker the surface, the older the journey. There is a quiet irony here that the chemistry which makes 3I Atlas unusual also makes it typical. Unusual in the specific ratios, in the dominance of carbon dioxide over water, but typical in the presence of tholins, in the detection of nickel and cyanide, in the basic inventory of molecules that appear whenever ice and radiation coexist. The laws of chemistry are the same everywhere. The quantum mechanics of molecular bonds does not change from star to star. Carbon dioxide behaves the same in the outskirts of a solar system 10 billion years ago as it does in our solar system today. The physics is universal, even when the outcomes vary, and so 3I Atlas, visitor from elsewhere, stranger from the deep, carries within its ice and dust the same fundamental building blocks that formed Earth, that form the Sun, that form every star and planet and comet in the galaxy. The atoms are recycled. The molecules are ancient. The chemistry is shared. What changes is the ratio, the abundance, the specific history encoded in the distribution of elements and isotopes. These are the fingerprints of origin, the clues that might someday tell us not where 3i Atlas came from, but what kind of place it came from, what kind of star, what kind of disk, what kind of beginning. For now, the molecules glow in the infrared, the spectrum is recorded, the data is archived, and the comet continues to sublimate, shedding 150 kilograms of material every second, releasing chemistry into the vacuum, offering its secrets to any instrument sensitive enough to look. Precision is a form of patience. 4,022 observations, 227 observatories, a span of time from May 15th to September 23rd, 2025. Each observation is a measurement of position where 3i Atlas appears against the background stars at a specific moment in time, recorded to fractions of an arc-second, time-stamped to fractions of a second. The observatories are scattered across the globe. Professional facilities atop mountains in Chile, Hawaii, Arizona, Spain. University telescopes operated by graduate students and postdoctoral researchers. Amateur astronomers with backyard instruments, contributing data points with care and diligence. The Minor Planet Center collects these observations, aggregates them, makes them available to researchers. The purpose of this accumulation is to refine the trajectory, to determine with increasing precision where the comet has been, where it is, where it will be. Gravitational physics is deterministic given an object's position and velocity at one moment. Its future path can be calculated exactly, provided all forces acting upon it are known. For most solar system objects, the dominant force is the sun's gravity. Planetary perturbations are secondary. Small corrections apply to the primary Keplerian orbit. The mathematics are well established. The predictions are reliable, but comets add complexity. As they sublimate, ejecting gas and dust into space, they experience a recoil force or rocket effect. Momentum must be conserved. If mass is ejected in one direction, the nucleus is pushed in the opposite direction. This produces what astronomers call non-gravitational acceleration. For active comets, this effect is measurable. It causes the comet to arrive at predicted positions slightly early or slightly late, depending on the direction of the jet relative to the comet's motion. Over weeks or months, the cumulative deviation from a purely gravitational trajectory becomes apparent in the positional data. The magnitude of non-gravitational acceleration depends on several factors: the rate of mass loss, the speed at which gas is ejected, the mass of the nucleus, and the geometry of the active regions on the surface. A small, highly active comet experiences large non-gravitational accelerations. A large, minimally active comet experiences small ones. For 3i Atlas, researchers expect to see non-gravitational acceleration. The comet is clearly active. Hubble images show a coma. Webb detects outgassing. The mass loss rate in early August is measured at 150 kilograms per second. Gas is streaming away from the surface at 440 meters per second. The conditions for a measurable rocket effect are present. The data is analyzed. Observations are compared to trajectories calculated using gravity alone. Residuals are computed, the difference between where the comet actually appears and where it should appear if only the sun and planets are pulling on it. The residuals are tiny. The upper limit on positional deviation is 0.028 arc-seconds. This is an extraordinarily small angle, roughly the apparent size of a coin viewed from 10 kilometers away. Across the several months of observations, accounting for the comet's distance from Earth, this translates to an upper limit on non-gravitational acceleration of less than 15 meters per day squared. This is effectively zero. To understand why this is surprising, consider the momentum balance. Each second, the comet ejects 150 kilograms of gas at 440 meters per second. The momentum carried away by this gas is the product of mass and velocity 66,000 kilogram meters per second, every second. By Newton's third law, the nucleus experiences an equal and opposite momentum change. If the nucleus has a small mass, this results in a noticeable acceleration. If the nucleus has a large mass, the acceleration is negligible. The fact that the observed non-gravitational acceleration is below the detection threshold implies that the nucleus must be extremely massive, massive enough that 66,000 kilogram-meters per second of thrust produces less than 15 meters per day squared of acceleration. The calculation is straightforward. Acceleration equals force divided by mass. Force, in this context, is the rate of momentum change, the mass loss rate multiplied by the ejection velocity. Rearranging the equation, mass equals force divided by acceleration. Given the observed outgassing and the upper limit on acceleration, the minimum mass of the nucleus is 33 billion metric tons, 33 trillion kilograms. At typical densities for cometary material around 500 kilograms per cubic meter, accounting for a mixture of ice and dust with significant porosity, this mass implies a minimum diameter of approximately 5 kilometers, 5,000 meters, more than 3 miles, larger than the previous upper estimates from Hubble imaging. At the high end of plausibility for a comet nucleus, though not impossible. Comet Hale-Bopp, one of the largest observed in modern times, has a nucleus estimated at 60 kilometers. Comet Bernardinelli-Bernstein, discovered in 2021, has a nucleus over 100 kilometers across, but these are exceptional objects, rare even among solar system comets. For an interstellar object, a 5-kilometer nucleus is unprecedented. Oumuamua was estimated at a few hundred meters across, though its exact size remains uncertain. Borisov's nucleus was less than 1 kilometer in diameter. If 3I Atlas is truly 5 kilometers or larger, it is 3 to 5 orders of magnitude more massive than the previous interstellar visitors. This creates a statistical problem. Interstellar objects are thought to be remnants of planet formation around other stars, ejected during the chaotic early phases when giant planets migrate and scatter smaller bodies. The size distribution of these ejected objects should follow a power law: many small objects for every large one. This is the pattern observed in our own solar system's asteroid and comet populations. Small bodies vastly outnumber large ones. If 3I Atlas is as massive as the data suggests, we should have detected hundreds or thousands of smaller interstellar objects before finding one this large. Yet we have only confirmed 3 interstellar visitors total. The statistics do not align. Either 3I Atlas is an outlier, a rare, chance detection of an unusually massive object, or our assumptions about the population of interstellar material are incorrect. Perhaps large objects are more common than models predict. Perhaps the ejection mechanisms favour massive bodies. Perhaps the detection biases are stronger than anticipated, making small objects nearly impossible to find. Or perhaps the mass estimate is wrong. Perhaps there is another explanation for the lack of measurable non-gravitational acceleration. Perhaps the outgassing is asymmetric in a way that cancels the rocket effect. Perhaps the jets are oriented such that the forces balance. Perhaps the surface activity is not uniformly distributed, creating torques that alter the rotation without producing net acceleration. These are possibilities. They cannot be ruled out with current data, but they require fine-tuning, require specific geometries and conditions. The simplest explanation, the one that requires the fewest assumptions, is that the nucleus is genuinely massive, and so the observations accumulate. The residuals remain consistent with zero. The comet moves along a trajectory sculpted by gravity alone, seemingly indifferent to the forces of its own sublimation, too massive to be pushed by the breath of its own decay. There is a stillness in this. An object travelling at tens of kilometers per second, shedding hundreds of kilograms every second, glowing visibly in telescopes around the world, and yet, in its motion, perfectly serene, unmoved, following the arc prescribed by the sun's gravity with such fidelity that no deviation can be measured. Only took billions of tons to achieve such calm. Mass is a form of inertia. It is resistance to change, a measure of how difficult it is to alter an object's state of motion. The more massive something is, the harder it is to push, to pull, to accelerate or decelerate. This is true for a pebble, for a planet, for a comet drifting through space. 33 billion tons. This is the lower limit on the mass of 3I Atlas, derived from the absence of measurable non-gravitational acceleration. It is not a direct measurement, no scale exists to weigh a comet, but an inference drawn from observations of motion and outgassing. The comet sheds mass continuously, expelling gas that should push it off course. The fact that no such push is detected means the nucleus must be heavy enough to absorb the thrust without noticeable effect. To put this mass in context, it is roughly equivalent to 30 billion cubic meters of water. If you could somehow gather all the water in a reservoir the size of a large city 10 kilometers on each side, 30 meters deep, you would approximate the mass of this comet's nucleus. At typical cometary density, accounting for a porous mixture of ice, rock, and organic compounds, 33 billion tons corresponds to a volume of approximately 65 billion cubic meters. A sphere of this volume has a diameter just over 5 kilometers. A somewhat elongated or irregular shape might measure 6 or 7 kilometers along the longest axis. 5 kilometers is not impossibly large for a comet. Solar system comets of this size exist, but they are rare. The vast majority of comets have nuclei smaller than 10 kilometers. Most are only a few kilometers across. Objects larger than 20 or 30 kilometers are exceptional. For an interstellar object, 5 kilometers is extraordinary. It makes 3I Atlas orders of magnitude more massive than the previous visitors. Oumuamua, the first confirmed interstellar object, was estimated to be roughly 200 meters along its longest dimension, small enough to fit inside a typical sports stadium. Its mass was perhaps a few million tons, depending on density and porosity. Exact values remain uncertain because Oumuamua was visible for only a short time and never developed a coma, making size estimates difficult. Borisov, the second interstellar object, was a clear comet with active outgassing. Its nucleus was measured at approximately 0.5 kilometer in diameter, with a mass on the order of hundreds of millions of tons. Larger than Oumuamua, but still modest compared to the largest solar system comets. If 3I Atlas is indeed 33 billion tons or more, it is roughly 100 times more massive than Borisov, 1,000 times more massive than Oumuamua, 3 to 5 orders of magnitude heavier. This discrepancy raises questions about the population of interstellar objects drifting through the galaxy. Theoretical models of planet formation predict that small bodies should vastly outnumber large ones. When planets form, they accrete material from a protoplanetary disk. The process is inefficient. For every large planet that forms, countless smaller objects are left over planetesimals, comets, asteroids. Many of these remnants are eventually ejected by gravitational interactions with the giant planets. The size distribution follows a power law. For every object of a given size, there are perhaps 10 or 100 or 1,000 objects half that size, depending on the specifics of the formation process. This pattern is observed in our solar system. Small asteroids outnumber large ones. Small comets outnumber large ones. If the same pattern holds for interstellar objects and there is no obvious reason it should not, then we should detect many small interstellar visitors before finding a large one. The small objects are more numerous. They should cross our detection threshold more frequently. Yet the observational record shows the opposite. 3 confirmed interstellar objects, 2 of them relatively small, the third, potentially, much larger. The progression does not follow expectations. One possibility is detection bias. Small objects are faint. They are difficult to detect unless they pass very close to Earth or become highly active. Oumuamua was discovered only because it passed within 24 million kilometers of Earth, close enough for reflected sunlight to make it briefly visible. Borisov was detected because it developed a bright coma while still relatively far from the Sun. Both discoveries were somewhat fortunate. If there are many small interstellar objects passing through the solar system undetected, the observed sample might be biased toward larger, brighter, more active bodies. This would explain why 3I Atlas appears disproportionately massive, but the bias would have to be severe. To explain the detection of one 5-kilometer object before detecting hundreds or thousands of smaller ones requires that small objects are nearly invisible to current surveys. This is possible, but suggests our understanding of the interstellar population is highly incomplete. Another possibility is that the size distribution of interstellar objects is different from the size distribution of bound solar system objects. Perhaps the ejection process preferentially ejects larger bodies. Perhaps close encounters with giant planets are more effective at flinging away massive comets than small ones. The dynamics are complex. The outcomes are not always intuitive. Or perhaps 3I Atlas is not typical. Perhaps it is an outlier, a statistical fluke, a rare massive object that happened to cross our path at a time when we had the instruments to detect it. Rare events occur. The universe is large. Given enough opportunities, even unlikely configurations eventually manifest. There is also the possibility, raised by a small number of researchers, that the mass estimate is incorrect, that some aspect of the comet's behavior produces the appearance of negligible non-gravitational acceleration without requiring enormous mass, asymmetric outgassing, rotation that averages out the thrust over time, complex surface topography that channels gas in ways that cancel net forces. These scenarios are not impossible, but they require specific conditions. They are less parsimonious than simply accepting that the nucleus is massive. For now, the data supports the interpretation 3I Atlas has a nucleus with a mass of at least 33 billion tons and a diameter of at least 5 kilometers. This makes it an anomaly among interstellar objects, a major anomaly, in the language of the researchers who have studied it most closely. And anomalies demand explanation. They disrupt models, they challenge assumptions, they force reconsideration of what is typical, what is rare, what is possible. There is a certain symmetry to this. That an object from elsewhere should prove difficult to categorize. That a visitor from interstellar space should defy the patterns established by objects native to our solar system. That the third interstellar object detected should be neither a smaller version of the first nor a larger version of the second, but something different in kind. Mass confers stability. A massive object resists perturbation. It follows its path with steadiness, unswayed by forces that would deflect lighter bodies. In this sense, 3I Atlas embodies its own mass. It moves with the serene indifference of something too large to be easily moved, too heavy to be casually redirected. 33 billion tons of ice and rock and organic molecules, assembled billions of years ago in the cold outskirts of another star's domain, now falling through our solar system with the inevitability of gravity, the patience of momentum, the silence of deep time made manifest in trajectory and mass. Only took an entire small moon's worth of material to travel this far, this long, this quietly. Statistics describe populations, not individuals. They tell us what to expect on average, across many instances, over long periods. They do not predict specific outcomes. A rare event, by definition, sometimes occurs. The question is whether the rarity challenges the model, or merely reflects the stochastic nature of observation. The population of interstellar objects is largely unknown. We have detected 3, from 3 data points. Drawing confident conclusions about billions of objects is an exercise in uncertainty quantified. Theoretical models attempt to estimate how many interstellar objects exist in the galaxy and how frequently they should pass through any given solar system. The estimates depend on assumptions how many planetary systems form, how many produce surplus planetesimals, how efficiently gravitational interactions eject material into interstellar space, how long ejected objects survive without colliding with stars or being recaptured by other systems, One widely cited estimate suggests that at any given moment, there are approximately 10 to the power of 15, a quadrillion interstellar objects larger than 100 meters drifting through the Milky Way. These objects are spread across a volume of space roughly 100,000 light-years in diameter. The average distance between them is measured in astronomical units, perhaps tens or hundreds of AU, given the Sun's motion through the galaxy and the typical velocities of interstellar objects. Models predict that a few such objects should pass within the orbit of Neptune each year. Most would be small meters to tens of meters across. Larger objects would be correspondingly rarer. If the size distribution follows a power law similar to that observed for asteroids and comets in our solar system, then for every object 10 kilometers across, there should be roughly 1,000 objects 1 kilometer across, 1 million objects 100 meters across, and so on. The exact slope of the power law varies depending on formation mechanisms, but the general pattern is steep, small objects vastly outnumber large ones. Under these assumptions, detecting a 5-kilometer interstellar object before detecting hundreds or thousands of smaller ones is improbable. Not impossible, random sampling occasionally produces unusual sequences, but improbable enough to warrant scrutiny. 3 scenarios could explain this discrepancy. First, detection bias is more severe than appreciated. Small interstellar objects are difficult to detect. They are faint, often inactive, and move quickly through the inner solar system. Survey telescopes like ATLAS, Pan-STARRS, and the Zwicky transient facilities scan the sky nightly, searching for moving objects, but their sensitivity is limited. An object must be bright enough and close enough to register above the noise. Oumuamua was discovered only because it passed within 0.16 astronomical units of Earth, about 60 times the distance to the Moon. At that range, even a small dark object reflects enough sunlight to be visible. Had it passed farther away, it might have gone unnoticed. Borisov developed a bright coma while still beyond Jupiter's orbit, making it easier to detect despite being farther from Earth. Its activity compensated for its small size. If most small interstellar objects are inactive and pass at greater distances, they would remain invisible to current surveys. Only the largest objects, or the most active, or the ones that happen to pass very close, would be detected. This selection effect could explain why the observed sample does not match the predicted size distribution. Second, the size distribution of interstellar objects might differ from expectations. Perhaps the ejection process preferentially ejects larger bodies. In dynamical simulations of planetary system evolution, close encounters between planets and smaller bodies transfer energy. The outcome depends on the mass ratio and the geometry of the encounter. For very small objects, the energy transfer might not be sufficient to achieve escape velocity. They are perturbed into different orbits but remain bound to the star. For intermediate-sized objects, the transfer is more efficient. They are flung outward with enough speed to escape. For very large objects, encounters are rarer. There are fewer of them to begin with, but when they do occur, the momentum transfer can still be substantial. If this process creates a size distribution for interstellar objects that is flatter than the distribution of bound objects, fewer small bodies relative to large ones, it would make the detection of a massive object like 3I Atlas less surprising. Third, 3I Atlas is an outlier, a statistical fluctuation. The universe is large. Galaxies contain billions of stars, trillions of planetary systems, quadrillions of ejected comets. Given enough opportunities, rare configurations occur. The fact that we have detected only 3 interstellar objects means the sample size is too small to rule out chance. If we detect 10 more interstellar objects over the next decade, and all of them are smaller than 1 kilometer, the anomaly will deepen. If we detect a mix of sizes consistent with a steep power law, 3E Atlas will be retrospectively understood as the fortunate detection of a rare large object. The data will resolve the question. Eventually. For now, the anomaly stands. 33 billion tons. 5 kilometers. Orders of magnitude more massive than the previous visitors. A major deviation from expectation. or a reminder that expectations based on 3 data points are provisional at best? There is a question underneath the statistics, a question not about numbers but about narrative. What does it mean for something to be anomalous? An anomaly is defined relative to a baseline, a norm, an expected distribution. But if the baseline is itself uncertain, if the norm is inferred from minimal data, then the concept of anomaly becomes unstable. Perhaps 3i Atlas is not anomalous. Perhaps it is typical, and the previous objects were unusually small. Perhaps the true population of interstellar visitors is dominated by kilometre-scale and larger bodies, and the small ones are so difficult to detect that we will never see more than a handful. Or perhaps each interstellar object is unique, shaped by the specific conditions of its birth system, its ejection, its journey. Perhaps there is no typical interstellar object, only a wide distribution of sizes, compositions, trajectories, each one carrying the fingerprint of its origin. The Vera C. Rubin Observatory, which began operations in 2025, will provide more data. It is designed to survey the entire visible sky every few nights, detecting faint, fast-moving objects that previous surveys might have missed. Over the next decade, it is expected to discover dozens or hundreds of interstellar objects, enough to begin mapping the population with confidence. Until then, the anomaly persists. 33 billion tons of mass moving through the solar system, resisting the forces of its own sublimation, challenging the models, prompting recalculations, only took 3 detections to reveal how little is known, only took one massive visitor to expose the uncertainty lurking in the statistics, the assumptions, the extrapolations from insufficient data. The ecliptic plane is a consequence of angular momentum. When the solar system formed 4.6 billion years ago, it condensed from a rotating cloud of gas and dust. As the cloud collapsed under its own gravity, conservation of angular momentum caused it to flatten into a disk. The Sun formed at the centre, the planets accreted within the disk. This is why, even now, the orbits of the major planets lie within a few degrees of the same plane. Most comets native to the solar system follow this pattern. More or less, short-period comets, which orbit the Sun in less than 200 years, tend to move in the same direction as the planet's prograde motion, following the original rotation of the protoplanetary disk. Long-period comets, arriving from the distant Oort cloud, can have any inclination. Some are prograde, some are retrograde, orbiting opposite to the planets, but there is no preference for alignment with the ecliptic. They arrive from all directions, isotropically distributed across the sky. Interstellar objects should show even less correlation with the ecliptic. They come from other star systems, formed in other disks oriented at arbitrary angles to our own. Their trajectories should be random relative to the plane of the solar system. No preference for low inclination. No preference for any particular direction. 3i Atlas does not follow this expectation. Its orbit is inclined at only a few degrees to the ecliptic plane. It moves within the disk of the solar system, nearly coplanar with the planets, but it travels retrograde opposite to the direction of planetary motion. It is moving backward through the solar system's traffic pattern, threading through the same flat space where Earth and Mars and Jupiter orbit, but going the wrong way. This combination is unusual, not impossible, not physically prohibited, but unusual enough to invite scrutiny. The trajectory can be described with precision. The orbital inclination is approximately 3 degrees. This means that if you could view the solar system edge-on with the ecliptic as a horizontal line, 3i Atlas would oscillate only slightly above and below that line as it passes through. It stays close to the plane. The argument of perihelion and the longitude of the ascending node technical parameters that describe the orientation of the orbit in 3-dimensional space place the comet's path such that it crosses the orbits of Mars and Venus. It does not intersect Earth's orbit. There is no collision risk, but the geometry brings it closer to some planets than others. On October 3rd, 2025, 3 Atlas passes within approximately 0.2 astronomical units of Mars. This is about 30 million kilometers, roughly 80 times the distance from Earth to the Moon. Not close in terrestrial terms, but close enough that spacecraft orbiting Mars might observe the comet. The Mars Reconnaissance Orbiter carries a camera called HiRISE High, resolution imaging science experiment capable of resolving details as small as 30 centimeters on the Martian surface. When pointed at objects in space, its resolution decreases with distance, but at 30 million kilometers, it might be able to discern the comet's nucleus if the coma is not too bright. If the geometry is favorable, if the observation is carefully planned, other spacecraft will also attempt to observe. Mars Express, the European Space Agency's orbiter, will turn its instruments toward the visitor. The ExoMars Trace Gas Orbiter will use spectrometers to analyze the comet's composition from a Martian vantage point. These observations are not guaranteed to succeed. The comet may be too faint. The viewing angles may be poor, but the opportunity is rare enough to justify the attempt. After the Mars encounter, 3I Atlas continues inward. On October 29th, it reaches perihelion, the closest point to the Sun. The distance is 1.36 astronomical units, roughly 203 million kilometers. This is between the orbits of Earth and Mars, closer to the Sun than Earth but farther than Venus. At perihelion, the comet will be travelling at its maximum speed, relative to the Sun approximately 68 kilometers per second. The solar heating will be at its most intense. The outgassing will reach its peak. The coma may expand to its largest size. The tail, if visible, may stretch across millions of kilometers, but from Earth, the comet will be invisible. At perihelion, 3I Atlas will be almost directly behind the Sun as seen from Earth. The solar elongation, the angular separation between the comet and the Sun in the sky, will be only a few degrees. Attempting to observe it would require pointing telescopes nearly at the Sun, which is dangerous and generally ineffective due to scattered light and atmospheric brightness. The comet will vanish into solar glare. For several weeks in late October and early November, it will be unobservable from Earth, hidden, occulted not by another body but by the overwhelming brightness of the Sun itself. This has prompted speculation. If one wished to perform a maneuver without being observed, perihelion behind the Sun would be an opportune moment. A spacecraft could fire engines, change velocity, alter trajectory, and the change might not be detected until the object emerged from solar glare weeks later. This is, of course, highly speculative. There is no evidence that 3I Atlas is anything other than a comet. The chemistry is comet-like. The activity is comet-like. The lack of non-gravitational acceleration suggests it is massive, not maneuvering. But the trajectory, the low inclination, the retrograde motion, the close passes to multiple planets invites questions. Why should an interstellar object be aligned with the ecliptic? Random chance allows it, but the probability is low. If interstellar objects approach from isotropic directions, most should have high inclinations. The fact that 3I Atlas has low inclination is, statistically, somewhat surprising. One explanation is simply luck. If enough interstellar objects pass through the solar system over time, eventually one will happen to arrive nearly in the ecliptic plane. The fact that we detected this one might be partly because its low inclination made it more likely to pass close to Earth or Mars, improving detectability. Another explanation involves galactic dynamics. The Milky Way has a disk structure, just like the solar system. Stars in the galactic disk tend to have low velocities perpendicular to the plane and higher velocities within it. If 3I Atlas originated from a star in the galactic disk and was ejected with a velocity similar to the velocity dispersion of disk stars, its motion through the galaxy might preferentially be within the galactic plane. But the galactic plane and the solar system's ecliptic plane are not aligned. The Sun's ecliptic is tilted at about 60 degrees relative to the galactic plane, so this explanation does not fully account for the observed geometry. A third possibility is that the alignment is not meaningful. that human pattern recognition imposes significance on configurations that are simply the outcome of physics and probability, that the trajectory is not guided, not aimed, not selected for any purpose, but merely the path that this particular comet happened to follow, based on its velocity vector upon entering the solar system and the gravitational influence of the Sun. The mathematics of orbital mechanics are deterministic. Given the comet's position and velocity at any moment, its future path is fixed. There is no agency in the trajectory, no intention, only the working out of gravitational forces and conservation laws, and yet the configuration persists as a curiosity. Retrograde through the ecliptic plane, close passes to Mars, Venus, potentially Jupiter on the outbound leg. A trajectory that, if one were designing a survey of the inner solar system, might resemble something deliberate. But comets do not design. They fall, they sublimate, they follow paths determined by gravity and velocity. And 3I Atlas, whatever its size, whatever its composition, is still falling backward through the disk, aligned with the planets, but moving against them. A visitor travelling the wrong direction down a one-way orbital road only took billions of years and trillions of kilometres to arrive here, at this angle, at this time, in this plane. An accident of geometry, a coincidence of trajectory, or simply the way this particular story unfolds. October arrives. The comet continues inward. Telescopes track its motion nightly. Ephemerides are updated. Predictions are refined. By early October, 3I Atlas is crossing the orbit of Mars, still approaching perihelion, still brightening as solar heating intensifies. On October 3rd, the geometry is favourable. The comet passes within 30 million kilometres of Mars, close enough that spacecraft in Martian orbit have a brief opportunity to observe an interstellar visitor from a unique vantage point. Close enough that the viewing angle, the lighting conditions, the relative positions might yield data unobtainable from Earth. The spacecraft are not designed for this purpose. The Mars Reconnaissance Orbiter, the Mars Express, the ExoMars Trace Gas Orbiter, all are planetary science missions, built to study Mars. Their instruments are optimized for observing a planet a few hundred or thousand kilometers below, not a comet 30 million kilometers away. But the instruments can be repurposed. Cameras can be pointed. Spectrometers can be aimed. Observations can be attempted. HiRISE, the high-resolution camera aboard the Mars Reconnaissance Orbiter, is capable of extraordinary detail when imaging the Martian surface. At its nominal operating distance, it can resolve features 30 centimeters across small enough to distinguish individual boulders, to map the tracks of rovers, to see details invisible to any other orbital camera. But resolution depends on distance. At 30 million kilometers, the resolving power decreases proportionally. Each pixel covers thousands of kilometers. The comet's nucleus, if it is 5 kilometers across, would occupy only a fraction of a single pixel. It would not be resolved. It would appear as a point of light, indistinguishable from a star except for its motion. But the coma might be visible. The cloud of gas and dust surrounding the nucleus extends for tens of thousands of kilometers by this point. Possibly more. If the coma is bright enough, if the exposure time is sufficient, HiRISE might capture an image showing the overall structure, the teardrop shape, the faint tail, the distribution of material around the nucleus. The observation is attempted. The spacecraft is commanded to slew, to point away from Mars toward a specific region of sky where 3I Atlas is predicted to be. The camera shutter opens. Photons that have travelled from the comet, reflected sunlight and scattered light from sublimating ice, strike the detector. The image is recorded, stored in onboard memory, eventually transmitted back to Earth. Whether the observation succeeds depends on factors not entirely predictable. The comet's brightness, the contrast against the background stars, the exposure settings chosen by the imaging team. The results will be analysed over the following days and weeks. Other instruments aboard Martian spacecraft also attempt observations. The Omega spectrometer on Mars Express, designed to map mineral composition on the Martian surface, is pointed toward the comet. It measures wavelengths in the visible and infrared, searching for spectral signatures of water, carbon dioxide, organics. The data is limited. The comet is faint, far away, but any data is valuable. The SPECAM ultraviolet spectrometer, also on Mars Express, attempts to detect hydrogen Lyman alpha emission, a characteristic signature of water vapor illuminated by sunlight. If the comet is outgassing water, even in small amounts, the hydrogen atoms dissociated from water molecules might glow at specific ultraviolet wavelengths detectable by SPECAM. The NOMAD spectrometer aboard the ExoMars Trace Gas Orbiter joins the effort. NOMAD is designed to study the Martian atmosphere with exceptional sensitivity, detecting trace gases at concentrations of parts per billion. Pointed at 3I Atlas, it searches for molecular signatures in the comet's coma carbon monoxide, methane, acetylene, any volatile that might be present and spectrally distinct. These observations are challenging. The instruments were not built for this. The signal is weak. The comet occupies a tiny fraction of the field of view. Background subtraction, calibration, data processing all require care and expertise. False detections are possible, null results are likely, but the opportunity is unique. Interstellar comets are rare. The chance to observe one from multiple spacecraft, from a non-terrestrial vantage point, from instruments with capabilities unavailable from Earth-based observatories, justifies the effort. The results, when they are eventually published, may be modest. Perhaps HiRISE captures only a faint smudge. Perhaps the spectrometers detect only marginal signals, consistent with but not definitively confirming the presence of specific molecules. Perhaps the data is inconclusive, limited by sensitivity and geometry. Or perhaps the observations reveal something unexpected, a burst of activity coinciding with the Mars encounter, an asymmetry in the coma suggesting localized outgassing, a spectral feature not seen in previous observations. The nature of discovery is that it cannot be predicted. You point the instruments, you collect the data, you analyze. Sometimes you find nothing, sometimes you find something new. As 3 Atlas moves past Mars and continues toward perihelion, other spacecraft prepare for their own observations. The JUICE mission, Jupiter Icy Moons Explorer, launched by the European Space Agency in 2023, currently en route to Jupiter, will attempt to observe the comet in November. By that time, 3I Atlas will have passed perihelion and begun its outward journey. It may be more active, shedding more gas and dust, brighter and easier to detect. JUICE carries a suite of instruments, cameras, spectrometers, a magnetometer, particle detectors. The spacecraft is still far from Jupiter, in a different part of the solar system than the comet, but the geometry may allow observations if the comet is bright enough. The imaging team will attempt to capture the coma and tail. The particle detectors might measure ions or dust grains if the spacecraft happens to pass through the extended trail of material shed by the comet. Back on Earth, ground-based telescopes continue their vigil. Observations from professional observatories, from university telescopes, from amateur astronomers equipped with CCD cameras and spectrographs. The data flows into databases. Positions are measured. Light curves are constructed, graphs showing how the comet's brightness changes over time. The brightness increases as the comet approaches perihelion. More solar heating, more sublimation, more material in the coma. The apparent magnitude decreases in astronomical convention. Brighter objects have lower magnitudes. By mid-October, 3I Atlas might be visible in medium-sized amateur telescopes, a faint fuzzy patch moving slowly against the stars. But then comes perihelion, late October. The comet is at its closest to the Sun, at its brightest, at its most active. And it is also nearly impossible to observe from Earth. The solar elongation is too small. The comet is lost in the glare. For a few weeks, it vanishes. The observations cease. The data stream pauses. The telescopes wait. The comet, indifferent to observation, continues to sublimate, continues to shed mass, continues to brighten, and then, as it begins to recede from the sun, begins to dim. The activity peaks unseen. The coma expands to its maximum extent beyond the view of any human instrument. The tail, if it is prominent, stretches across millions of kilometers in a direction determined by solar wind and radiation pressure. Unobserved, unmeasured, known only through later inference, only took travelling billions of kilometers, only took approaching within 200 million kilometers of a star, only took timing the arrival such that the moment of greatest activity coincides with invisibility from the civilization attempting to study it, a coincidence of geometry, a reminder that the universe does not arrange itself for convenient observation. There is a geometry to invisibility. When an object passes nearly between an observer and a light source vastly brighter than itself, it vanishes not because it ceases to exist, but because the contrast renders it undetectable. The light source overwhelms. The object is drowned in glare. For 3i Atlas, the light source is the Sun. On October 29th, 2025, the comet reaches perihelion at a distance of 1.36 astronomical units. From Earth's perspective, the angular separation between the comet and the Sun is minimal, less than 3 degrees. Attempting to observe the comet would require pointing telescopes within a few degrees of the Sun's position in the sky. This is not impossible in principle. Solar observatories do it routinely, using coronagraphs instruments that block the Sun's direct light to reveal the faint corona and any objects passing nearby. The SOHO spacecraft, positioned at the L1 Lagrange point between Earth and Sun, has discovered thousands of comets passing through its field of view, small sun-grazing objects that plunge into the solar atmosphere and often do not survive. But 3i Atlas is not a sun-grazer. It passes well outside the Sun's corona, at a distance of 200 million kilometers. At that distance, it is not in SOHO's field of view. It is not close enough to the Sun's limb to be captured by coronographic imaging. It occupies a gap in observational capability too far from the Sun to be seen in coronagraphs, too close to the Sun in angular terms to be observed by conventional telescopes. Ground-based telescopes cannot safely point within a few degrees of the Sun. The risk of damage to instruments and detectors is too high. Even if filters are used, even if precautions are taken, the scattered sunlight in Earth's atmosphere creates a background too bright to see faint comets. The sky near the Sun is blue and brilliant. Comets are faint and greyish. The contrast is insurmountable. Space telescopes fare slightly better. Without atmospheric scattering, the background is darker, but even in space, pointing close to the Sun is hazardous. Sensitive instruments can be damaged by direct sunlight. Thermal control becomes difficult. Most space telescopes have keep-out zones regions of the sky they are not allowed to point toward to avoid sun exposure, and so, for approximately 3 weeks in late October and early November, 3i Atlas is effectively invisible to most of humanity's observational apparatus. It continues along its trajectory, governed by gravity and momentum, but it does so unobserved. This period of invisibility has prompted certain speculations. If one were to imagine purely as a thought experiment that 3i Atlas were not a natural comet but a spacecraft, perihelion behind the Sun would be an opportune moment to alter trajectory without detection. An engine could fire. Velocity could change. The spacecraft could decelerate, entering a bound orbit around the Sun, or accelerate, adjusting its path toward a specific destination. The maneuver would be hidden from Earth-based observers. By the time the object emerged from solar glare in December, weeks would have passed. The trajectory could be recalculated based on new observations, but attributing any deviations to a specific maneuver performed at a specific time would be difficult. The period of invisibility creates an observational gap. This is, of course, speculation built on speculation. There is no evidence that 3i Atlas is anything other than a comet. The detected chemistry carbon dioxide, water, cyanide. nickel is consistent with natural cometary composition. The lack of measurable non-gravitational acceleration suggests a massive nucleus, not active propulsion. The trajectory, while unusual in its alignment with the ecliptic, can be explained by gravitational dynamics without invoking artificial maneuvers, but the speculation persists in certain circles, articulated most prominently by a small number of researchers who argue that the possibility should not be dismissed without investigation, that the history of science includes instances where unlikely hypotheses proved correct, that the consequences of missing evidence of extraterrestrial technology, if such evidence exists, are significant enough to warrant scrutiny even of low-probability scenarios. The counter-argument is equally straightforward. Extraordinary claims require extraordinary evidence, and the evidence for 3I Atlas being anything other than a comet is absent. The speculation is not prohibited, but it should not be mistaken for equivalence with the scientific consensus, which treats the object as a natural interstellar comet of unusual but not impossible characteristics. Regardless of these debates, the comet itself continues unaffected. At perihelion, the solar flux is intense. The surface temperature of the nucleus, where sunlight strikes directly, may reach temperatures above 200 Kelvin, warm enough for water ice to sublimate rapidly, though still well below the freezing point by terrestrial standards. The outgassing intensifies. Gas jets stream from the sunlit hemisphere, carrying dust particles into space. The rocket effect, negligible due to the comet's large mass, is at its maximum. If any deviation from a purely gravitational trajectory were to occur, it would be most likely now, when the forces are strongest. But the observations before perihelion and the observations after, once the comet emerges from solar glare, will allow researchers to check for deviations. If the trajectory changes in a way inconsistent with the expected rocket effect from measured outgassing, that would be significant. If the path after perihelion matches predictions based on gravity and pre-perihelion observations, that would support the natural comet hypothesis. The data will resolve this, eventually. Patience is required. The comet must travel far enough from the Sun that observations become possible again. Telescopes must reacquire the target. Positions must be measured. Calculations must be performed. In early December, 3 Atlas emerges from solar glare. The elongation increases. The comet is now receding from the Sun, moving outward, dimming as the distance grows and the solar heating decreases. Observers in the southern hemisphere have the best viewing geometry. Telescopes in Chile, Australia, South Africa begin to track the object again. The positions are measured. The trajectory is recalculated. Preliminary results suggest no major deviations. The comet appears to be following the expected path, decelerating as the Sun's gravity pulls it back, but still moving fast enough to escape, still on a hyperbolic trajectory. More data is needed, more observations over more nights. The error bars on the trajectory will shrink as the dataset grows. Any anomalies, if they exist, will become apparent, or the trajectory will confirm expectations, and the speculation will be, once again, deferred. For now, in late October, at perihelion, the comet is simply invisible, hidden not by intention or stealth, but by the geometry of light and distance, sublimating in solitude. Warming under a star it will never orbit again. Experiencing the closest approach to stellar heat it has felt in millions or billions of years, and doing so unobserved, unrecorded, known only through inference and calculation. The universe is full of events no one witnesses, supernovae in distant galaxies, their light not yet arrived, asteroids colliding in the outer solar system, impacts recorded only in the slow rearrangement of orbits, comets brightening and fading in the cold beyond Neptune, sublimating feebly in the weak sunlight, never discovered because they never come close enough or bright enough. 3 Atlas, at perihelion, joins this category briefly, an event occurring beyond direct observation. The data will come later, the analysis will follow. But the moment itself, the peak of solar heating, the maximum outgassing, the closest approach happens in the gap between observations, in the interval where calculation substitutes for measurement, where models predict what instruments cannot see. Only took travelling across interstellar space, only took falling into a new solar system, only took arriving at the moment of greatest interest when the geometry makes observation impossible. A coincidence of timing, a reminder that nature does not perform for audiences. Ice remembers, not in the sense of conscious memory, but in the sense that its composition encodes information about the conditions under which it formed, the ratio of isotopes, the abundance of different molecular species, the presence or absence of trace compounds. These are records, frozen and preserved, of the temperature, pressure, and chemistry of the environment where the ice condensed from gas billions of years ago. When the James Webb Space Telescope and other instruments analyze the spectrum of 3I Atlas, they are reading this record. Each detected molecule is a clue. Each ratio is a constraint on the formation environment. The carbon dioxide dominance is the most striking feature. In our solar system, water ice is typically the most abundant volatile in comets. Carbon dioxide is present, sometimes in substantial quantities, but usually secondary. The fact that 3I Atlas has comparable or greater amounts of CO2 relative to water suggests formation beyond the carbon dioxide frost line, the distance from its parent star where temperatures were cold enough for carbon dioxide to condense into solid ice. In our solar system, the CO2 frost line is located somewhere beyond the orbit of Mars, perhaps around 3 astronomical units from the Sun, depending on the specific conditions in the early solar nebula. Comets that formed beyond this line would naturally incorporate more carbon dioxide. But even in the outer solar system, water is generally more abundant because oxygen preferentially bonds with hydrogen to form water rather than with carbon to form CO2. For 3I Atlas to be so rich in carbon dioxide, either the parent protoplanetary disk had an unusual carbon-to-oxygen ratio, or the comet formed in an extremely cold region where even water ice was scarce, and carbon dioxide was the dominant condensable volatile. Another possibility is that the parent star was less luminous than the Sun. A dimmer star would have frost lines closer in. The habitable zone, the region where liquid water could exist on a planetary surface, would be closer to the star. The carbon dioxide frost line would also be closer. A comet forming in the outer reaches of such a system might naturally be enriched in CO2. Stars with lower metallicity, less abundance of elements heavier than hydrogen and helium are common in the galaxy's thick disk and halo. These are older stars, formed when the Milky Way was younger and had undergone fewer generations of stellar nucleosynthesis. If 3I Atlas originated from such a star, its chemistry might reflect the lower metallicity environment. The presence of carbon monoxide adds another layer. CO is even more volatile than CO2, sublimating at temperatures below 100 Kelvin. Its detection suggests that some regions of the comet's nucleus have remained extremely cold, perhaps never warmed above 100 Kelvin even during formation, or the CO is a product of photodissociation carbon dioxide molecules broken apart by ultraviolet light, producing carbon monoxide and atomic oxygen. Water is detected, but in smaller amounts than in typical solar system comets. Water ice, water vapour. The spectral lines are present, measurable, but not dominant. This is consistent with formation in a very cold environment, or with preferential loss of water during the comet's long journey through interstellar space. Water ice is more susceptible to photodissociation than carbon dioxide ice. Ultraviolet photons from distant stars, cosmic ray impacts, can break the molecular bonds in water, releasing hydrogen and oxygen atoms. Over millions of years, this process can erode the surface layers of a comet. The hydrogen, being very light, escapes into space. The oxygen may recombine with carbon to form CO or CO2, or it may form other compounds. If 3I Atlas has been drifting through interstellar space for billions of years, its surface would have been continuously irradiated. The outer layers, perhaps the outermost meters or tens of meters, might be depleted in water relative to the interior. The carbon dioxide, more stable under irradiation, would remain. The observed CO2-H2O ratio might not reflect the bulk composition of the nucleus, but rather the composition of the surface layers currently sublimating. This hypothesis could be tested, in principle. If the comet's activity continues to increase as it approaches perihelion, exposing deeper layers of ice, the chemical composition might shift. More water might appear in the spectra. The ratio might change. Observers will watch for this. Carbonyl sulfide OCS is another trace molecule detected. Sulfur is a relatively uncommon element in comets, present at concentrations of less than 1% by mass. The fact that a sulfur-bearing molecule is detectable suggests that 3I Atlas's parent disk had sulfur available during formation, incorporated into ices along with carbon and oxygen. Sulfur compounds are of particular interest in astrobiology. On Earth, sulfur plays a role in certain metabolic pathways, particularly in environments where oxygen is scarce. Detecting sulfur in an interstellar comet is not evidence of biology. Sulfur is a common element, and its presence in comets is well documented, but it adds to the inventory of chemical complexity. The tholins, the reddish organic compounds that give the comet its colour, are not single molecules but complex mixtures. They form when simpler hydrocarbons and nitriles are exposed to radiation. The exact structure of tholins varies depending on the starting materials and the type of radiation, but they generally consist of long chains or rings of carbon atoms with hydrogen, nitrogen, and oxygen attached. Tholins are found throughout the outer solar system. They are the reason Pluto's surface is tan and reddish. They coat the surfaces of Titan's lakes and dunes. They are present in the dust of comet tails. They are ubiquitous wherever organic molecules and radiation coexist over long timescales. If 3I Atlas has been irradiated for billions of years, its surface tholins could be among the oldest organic compounds accessible to observation. They represent a fossil record of interstellar chemistry, of processes occurring in the cold dark between stars, of the slow transformation of simple molecules into complex ones driven by nothing more than time and radiation. There is a question that persists in the analysis of these molecules: to what extent does the observed chemistry reflect the comet's origin, and to what extent does it reflect its journey? A comet is not a static object. It changes. Surface layers are eroded by cosmic rays. Molecules are photodissociated by starlight. Micrometeoroids impact and vaporize tiny amounts of material. Over millions of years, these processes can alter the surface composition substantially. The interior of the comet, shielded by overlying material, may be better preserved, but the interior is not directly observable. What we see, what the spectrometers measure, is the material currently sublimating from the surface. This is a mixture of original material and processed material, of chemistry from formation and chemistry from alteration. Disentangling these contributions is difficult. It requires models, assumptions, comparisons with other comets. It requires understanding the rates of photodissociation, the depth to which cosmic rays penetrate, the thermal conductivity of ice and dust mixtures. The James Webb observations provide a snapshot, the composition at one moment in time, as the comet approaches perihelion. Future observations, as the comet recedes and different layers are exposed, may provide additional snapshots. Comparing these snapshots might reveal changes, might hint at compositional gradients, might offer clues about the interior, but some questions will remain unanswered. The parent star is unknown. The formation conditions can only be inferred. The history of the journey is lost to time. The comet carries its secrets in the structure of its ice, in the ratios of its molecules, in the colour of its dust. We read what we can, we infer what we must, and we acknowledge the limits of what frozen chemistry can tell us about events that occurred billions of years ago, light years away, in a system we will never see. Only took 4.6 billion years, give or take, for this ice to condense, to be ejected, to drift, to arrive here, carrying molecules that remember a star that may no longer exist. Preserving chemistry from an era of the galaxy we study only through inference and distant light. Age is difficult to measure for objects that do not emit their own light. Stars can be dated by their spectral characteristics, by the composition of their atmospheres, by their position on the Hertzsprung-Russell diagram. Planets and moons can be dated through radiometric analysis of rocks, measuring the decay of radioactive isotopes with known half-lives. But comets are frozen volatiles and dust, pristine samples of the material from which they formed, never heated enough to melt or differentiate, never processed through geological cycles that reset radiometric clocks. For 3I Atlas, direct age determination is impossible without a sample return mission, without bringing material back to laboratories on Earth where isotopic ratios can be measured with precision. Such a mission is not planned. The comet is moving too fast, on a hyperbolic trajectory that will carry it out of the solar system within a few years. Rendezvousing with it, matching its velocity, collecting a sample, and returning to Earth would require propulsion systems and mission durations beyond current capabilities. So age must be inferred indirectly, through dynamical arguments, through chemical clues, through statistical reasoning about the population of interstellar objects and the history of star formation in the galaxy. One approach involves tracing the comet's trajectory backward through the Milky Way. If the path can be reconstructed over millions of years, accounting for gravitational perturbations from stars and molecular clouds, it might be possible to identify regions of the galaxy the comet has passed through, and from that, to constrain when and where it might have been ejected from its parent system. This is extraordinarily difficult. The galaxy is a dynamic environment. Stars move. The Sun orbits the galactic center at approximately 220 kilometers per second, completing one orbit every 230 million years. Other stars have different orbital speeds and directions. Relative velocities between stars can be tens of kilometers per second. 3I Atlas entered the solar system at 58 kilometers per second relative to the Sun. Subtracting the Sun's motion through the galaxy, the comet's velocity in the galactic rest frame can be estimated. This velocity places constraints on which populations of stars the comet might be associated with. Stars in the Milky Way's thin disk, the flat region, where most young stars reside, including the Sun, have relatively low velocities perpendicular to the galactic plane. Stars in the thick disk and older, more diffuse population above and below the thin disk have higher velocity dispersions. Stars in the galactic halo, the oldest and most metal-poor, have even higher velocities and more eccentric orbits. The velocity of 3I Atlas suggests it could belong to either the thin disk or the thick disk. If it is a thick disk object, it is likely much older. Thick disk stars formed primarily in the early history of the galaxy, 7 to 10 billion years ago. If 3I Atlas was ejected from a planetary system around a thick disk star, the comet itself could be 7 billion years old or more. 7 billion years is older than the Sun, older than Earth, older than any rock found on Earth's surface, older than the oldest meteorites in our collections. If this estimate is correct, 3I Atlas formed when the Milky Way was younger, when the rate of star formation was higher, when the abundance of heavy elements was lower. A comet that old would have witnessed much of the galaxy's history. It would have been drifting through interstellar space when the Sun condensed from a molecular cloud 4.6 billion years ago. It would have been travelling the dark lanes between stars when Earth formed, when life arose, when the first multicellular organisms appeared, when dinosaurs walked, when humans evolved. All of that history, all of Earth's history occurring while this frozen mass moved silently through the void, unchanged except for the slow erosion of cosmic rays and the rare impact of interstellar dust grains. Of course, this is uncertain. The comet might be younger. It might have been ejected from a thin disk star only a few billion years ago, or even less. The velocity does not uniquely determine the age. Multiple scenarios are consistent with the observations, but the possibility of great age is worth contemplating. If 3I Atlas is 7 billion years old, it predates not only the solar system, but also a significant fraction of the planetary systems currently in existence. It would be one of the oldest comets ever observed, a relic from the early epoch of planet formation in the galaxy. The chemistry offers some additional clues. The carbon dioxide dominance could indicate formation around a low metallicity star, which would favour an older age. Stars that formed when the galaxy was young had less metal content, fewer elements heavier than hydrogen and helium, because there had been fewer generations of supernovae to enrich the interstellar medium with heavy elements. A low metallicity protoplanetary disk would have different chemistry. Less carbon, less oxygen, less silicon and iron relative to hydrogen. The ices that condense in such a disk might have different ratios. The interpretation is not straightforward, but it is plausible that the observed CO2-H2O ratio reflects formation in a metal-poor environment. The tholins, the organic compounds that redden the surface, also carry a temporal signature. Tholins form slowly under irradiation. The degree of reddening, the depth of the colour, can be related, though not precisely, to the duration of exposure. Older objects, irradiated for longer periods, tend to be redder and darker. 3I Atlas has a reddish colour similar to other long-irradiated bodies in the outer solar system. This is consistent with significant age, though it does not prove it. A younger object could also develop reddish tholins if the radiation dose rate were high, or if the starting material were particularly susceptible to tholin formation. The surface texture, if it could be observed at high resolution, might also offer clues. Billions of years of micrometeoroid bombardment would create a regolith, a layer of fragmented material on the surface. The depth and structure of this regolith would depend on the impact rate in interstellar space and the duration of exposure. But the comet is too far away, too small, for such details to be resolved with current instruments. Another consideration is the survival time. How long can a comet survive in interstellar space before it is destroyed or altered beyond recognition? Cosmic rays slowly erode the surface. High-energy particles knock atoms out of the ice lattice, creating defects, breaking bonds, sputtering material into space. The rate is slow, perhaps a few meters of erosion per billion years, depending on the energy spectrum of cosmic rays in the interstellar medium. A comet with a radius of a few kilometers could survive billions of years before being significantly eroded. Collisions with interstellar dust are another hazard. The density of dust in the interstellar medium is low, perhaps 1 grain per cubic kilometer, but at relative velocities of tens of kilometers per second. Even small grains carry significant kinetic energy. Over billions of years, the cumulative effect of countless tiny impacts could erode or fracture the surface. Gravitational encounters with stars are rare but possible. A close pass to a star could tidally disrupt a comet, tearing it apart if the tidal forces exceed the comet's self-gravity. But space is vast, and stars are far apart. The probability of a close enough encounter to cause disruption is low over timescales of billions of years. Recapture by another star system is also possible. If the comet passes through a stellar system with massive planets, a gravitational assist could alter its trajectory, potentially capturing it into orbit around the new star. But again, the probability is low. Most interstellar objects pass through stellar systems without close encounters, so a comet can, in principle, survive for billions of years in interstellar space. It is eroded slowly, it is altered gradually, but it persists. Ice is stable at the temperatures of the interstellar medium a few Kelvin above absolute zero. Without a nearby star to heat it, without an atmosphere to erode it, a comet can drift indefinitely. If 3I Atlas is 7 billion years old, it has been drifting for most of the current age of the universe. The universe is 13.8 billion years old. 7 billion years is roughly half that span. The comet would have formed when the universe was less than half its current age, when galaxies were still assembling, when the cosmic star formation rate was near its peak. It is possible, it is perhaps even likely, given the velocity and the galactic population it seems to belong to, but it is not certain. Age estimates based on dynamics and chemistry are uncertain. The comet might be younger, or it might be even older. A survivor from the very earliest generations of planet formation in the Milky Way. What is certain is that it is old. Older than anything humans have touched. Older than any artifact, any fossil, any terrestrial material. It is a visitor from deep time, carrying ice that condensed before the sun ignited, before Earth coalesced, before life began. Only took 7 billion years, more or less, to travel from there to here. A duration incomprehensible in human terms, longer than the existence of complex life on Earth, longer than the Earth has had continents, long enough that entire lineages of stars have been born, lived, and died while this comet drifted silently through the dark. There are questions that observations cannot answer, not because the instruments are insufficiently sensitive, not because the methods are flawed, but because the phenomena themselves are ambiguous. Multiple explanations fit the data equally well. Uncertainty is irreducible without additional information that may not be obtainable. For 3I Atlas, one such question concerns the lack of measurable non-gravitational acceleration. The standard interpretation is straightforward. The comet is massive, 33 billion tons or more, a nucleus 5 kilometers in diameter or larger. The outgassing, though substantial at 150 kilograms per second, produces negligible thrust when applied to such a large mass. The rocket effect exists but is too small to measure given current observational precision. This explanation is parsimonious. It requires no additional assumptions. It is consistent with the observed chemistry, the visible coma, the spectroscopic detection of sublimating volatiles. A large, active comet behaves exactly as 3I Atlas appears to behave, but there are alternative explanations. One possibility is that the outgassing is symmetric. If gas jets are distributed uniformly across the sunlit hemisphere, or if active regions are positioned such that their thrust vectors cancel, the net force on the nucleus could be zero even if the individual jets are strong. This would produce no measurable acceleration despite significant mass loss. This scenario requires specific geometry. It is not impossible some solar system comets show nearly symmetric outgassing, but it is not the norm. Most comets have localized active regions, jets emanating from specific spots on the surface where subsurface ice is exposed or where thermal conductivity is higher. These jets produce asymmetric forces, detectable as non-gravitational accelerations. For 3I Atlas to exhibit symmetric outgassing would require either a very uniform surface composition or a rotation period and axis orientation that average out the asymmetries over time. The rotation period is not yet well constrained. Measuring it requires detecting periodic variations in brightness or spectroscopic features, and the comet is faint enough that such variations are difficult to discern. Another possibility is that the non-gravitational acceleration is oriented perpendicular to the orbital plane, or in some other direction that does not produce easily measurable positional deviations in the plane of the sky. Astrometric observations primarily measure position in 2 dimensions, right ascension and declination. Accelerations perpendicular to the line of sight or perpendicular to the orbital plane can exist, without producing large residuals in these coordinates. This is less likely for a comet with the observed outgassing, but it cannot be ruled out without 3-dimensional velocity measurements or radial velocity data that tracks motion toward or away from Earth. A third possibility, raised by a small number of researchers, is that the lack of measurable acceleration is itself significant, that it indicates something other than natural outgassing is at work, that a massive object should show at least some deviation, and the fact that none is observed might suggest the outgassing is not producing thrust in the expected manner, or that the object is compensating for the thrust through some other mechanism. This line of reasoning leads to speculative territory. If the object were artificial, if it were a spacecraft rather than a comet, it could actively stabilize its trajectory, using thrusters or other systems to counteract the forces from outgassing or to maintain a specific path. The chemistry detected by Webb and other instruments could be material accumulated on the surface during the long journey through interstellar space, ice and dust coating an underlying structure. This hypothesis is not favoured by the scientific community. It requires assumptions that are not supported by the data. The chemical composition is consistent with natural comets. The morphology is consistent with natural comets. The activity is consistent with natural sublimation driven by solar heating. There is no evidence of artificial structures, no anomalous emissions, no deviations from expected behaviour that cannot be explained by natural processes, but the hypothesis is discussed, primarily because the consequences of dismissing it prematurely if it were true are considered significant. The argument is not that 3I Atlas is likely to be artificial, but that the possibility should not be excluded without investigation, that observation should be made with the intent to test the hypothesis, even if the expected result is negative. This reflects a broad attention in the study of interstellar objects. On one hand, the principle of parsimony. Occam's razor suggests that natural explanations should be preferred unless the evidence clearly favours alternatives. Comets are known to exist. Interstellar comets are expected based on models of planet formation. Detecting an interstellar comet is not surprising. On the other hand, the search for extraterrestrial intelligence SETI has spent decades looking for artificial signals from other civilizations. The discovery of an interstellar object passing through our solar system offers a rare opportunity to apply observational scrutiny to something that has travelled between stars. Even if the probability of artificial origin is low, the implications of a positive detection are profound enough to justify careful analysis. The debate is unlikely to be resolved definitively. Absent a sample return mission, absent close-up imaging showing artificial structures or natural geological features, the ambiguity persists. Different researchers weigh the evidence differently. Some see an unusually large but entirely natural comet. Others see an object worthy of continued scrutiny for any sign of anomalous behaviour. For the comet itself, the debate is irrelevant. It continues along its trajectory, governed by gravity and momentum. It sublimates according to the physics of ice and sunlight. It does not respond to speculation, does not alter its path based on the hypotheses constructed around it. In December, as the comet emerges from solar glare and observations resume, the trajectory will be recalculated. Any deviations from the predicted path will be noted. If the trajectory matches expectations based on gravity alone, the natural comet interpretation will be further supported. If deviations appear that cannot be explained by known forces, the discussion will intensify. The data will accumulate. The uncertainties will narrow. Some questions will be answered, others will remain open, limited by the quality of observations or the ambiguity inherent in the phenomena. This is the nature of studying distant objects. We work with reflected light, with spectroscopic signatures, with positional measurements. We infer composition, structure, history. We build models and test them against observations. We acknowledge what we know and what we do not. 3I Atlas is massive, or its outgassing is unusually symmetric. It is 7 billion years old or younger. It formed around a low metallicity star or a more typical one. It is entirely natural, or it is something else. The data constrains but does not uniquely determine. The observations inform but do not fully resolve. And so the comet remains, in some sense, mysterious. Not because it is mysterious in its behaviour. It behaves as comets behave, but because the specific details of its origin, its journey, its composition remain uncertain. Because we see it from a distance, briefly, as it passes through, because it does not stay long enough for detailed study, because it carries its history within ice we cannot sample. Within chemistry, we can only glimpse through sublimation. Only took travelling 4.5 astronomical units inward. only took approaching within observation range, only took beginning to sublimate, to reveal enough chemistry to raise questions that current methods cannot definitively answer. A visitor that teaches as much about the limits of observation as about the object itself. Departure is inevitable. The trajectory is hyperbolic. The velocity is sufficient. Gravity bends the path but cannot close it. After perihelion, after the close approach to the Sun, after the maximum heating and the peak of activity, 3i Atlas begins the slow process of leaving. Slow is a relative term. The comet is still moving at tens of kilometers per second, but compared to the inward fall, when velocity increased steadily as gravitational potential energy converted to kinetic energy, the outward journey feels like deceleration. The Sun's gravity pulls back, the speed decreases, kinetic energy converts back to potential energy. The arc straightens as the distance grows. In December 2025, observations resume. The comet has emerged from solar glare. It is visible again from Earth, though dimmer now, receding, the coma shrinking as solar heating decreases and outgassing slows. The telescopes reacquire it. Positions are measured. The trajectory is refined. The path matches predictions. No major deviations are apparent. The comet continues along the expected hyperbolic trajectory, decelerating under the Sun's gravity but still moving fast enough to escape. The models hold. The dynamics are as expected. By January 2026, 3i Atlas is beyond the orbit of Mars on its outbound leg. The distance from the Sun is increasing. The temperature is dropping. The sublimation of carbon dioxide slows. The coma fades. The comet becomes fainter, harder to observe. Only the largest telescopes can track it now. In March 2026, the comet crosses the orbit of Jupiter, outbound. This is a milestone. Beyond this point, few solar system comets remain active. The sunlight is too weak. The temperatures are too low. Water ice is stable. Even carbon dioxide ice sublimates only weakly. The comet will likely become quiescent, appearing once again as a faint point of light rather than a diffuse coma. The opportunity for observation is fading. Each week, the comet grows fainter. Each month, fewer telescopes are capable of detecting it. By mid-2026, only the most sensitive instruments, large ground-based observatories, space telescopes with long integration times can still measure its position. The Vera C, Rubin Observatory, with its wide field of view and sensitive detector, continues to track the comet longer than most. The data flows into the archives, positions, magnitudes, occasional spectra when the signal-to-noise allows. The dataset grows, documenting the slow fade as the comet recedes. There is a poignancy to this. An object that has travelled for billions of years, that has crossed light-years of interstellar space, that has approached a new star and briefly glowed under its warmth, now returns to the cold. The visit lasts only months. The journey continues for eons. By late 2026, 3i Atlas will be beyond Saturn's orbit, fainter still, possibly undetectable except in the longest exposures. The last observations will be made, the final positions recorded, and then the comet will fade below the detection threshold, lost not because it has ceased to exist, but because it is too far and too faint for current instruments to see. It will continue outward, through the orbit of Uranus, through the orbit of Neptune, into the region where the Kuiper belt lies, though 3i Atlas will not linger there. Its velocity is too high. It will pass through the outer solar system in a matter of years, while native Kuiper belt objects take centuries to complete a single orbit. Beyond Neptune, the comet enters the realm of the scattered disk and eventually the inner Oort cloud, regions populated by icy bodies in distant eccentric orbits. But 3i Atlas will not join this population. It is not bound. It is leaving. At some point perhaps in the 2030s or 2040s, depending on exact trajectory, it will cross the heliopause, the boundary where the solar wind's influence ends and the interstellar medium begins. This boundary is not sharp. It fluctuates with solar activity, but it marks the transition from the Sun's domain to the space between stars. Voyager 1 and Voyager 2, humanity's most distant spacecraft, crossed the heliopause in 2012 and 2018 respectively. They are still transmitting data, still operating, though their power sources will eventually decay and contact will be lost. 3i Atlas will cross the same boundary, but it will do so in silence. No instruments aboard, no transmissions, no record of the crossing except the trajectory extrapolated from the last observations years earlier. After that, interstellar space. The comet will return to the environment it has known for most of its existence. The temperature will drop to a few Kelvin. The density of matter will decrease to 1 atom per cubic centimetre. The starlight will dim to the faint collective glow of the Milky Way. The comet will once again be in the dark, the cold, the void. Its velocity relative to the Sun will asymptotically approach 58 kilometers per second, the hyperbolic excess velocity, the speed it had upon entering the solar system. This velocity will carry it outward indefinitely. In 10,000 years, it will be light years away. In 1,000,000 years, it will have traversed a significant fraction of the distance between stars. In 1,000,000,000 years, it might encounter another stellar system, might fall inward toward another sun, might briefly glow again under different light, or it might not. The galaxy is vast, stars are far apart. The probability of a specific comet encountering a specific star over any reasonable timescale is low. 3i Atlas may drift for billions more years without another close stellar encounter. It may travel the length and breadth of the Milky Way, a silent wanderer, a frozen archive of ancient chemistry, moving through the dark until the stars themselves burn out. There is a symmetry to this. The comet arrived from interstellar space. It passes through the solar system. It returns to interstellar space. The visit is an interruption in a much longer journey, a brief detour into warmth and light, a momentary brightening before the return to cold. For humanity, the visit offers a glimpse, a chance to study material from another stellar system, a rare opportunity to measure, to analyze, to learn. The data collected spectra, positions, images will be studied for years, papers will be written, models will be refined, hypotheses will be tested, but the comet itself will be gone. It will continue its journey, indifferent to the attention it has received, unaffected by the debates it has prompted. It is not here for us. It is here because its trajectory, calculated by gravity and velocity over billions of years, happened to intersect the solar system at this moment in cosmic history. And then it leaves, not because the visit is complete, not because any purpose has been fulfilled, but because the trajectory demands it. The hyperbola opens outward, the path leads away, gravity bends but does not bind. In the cold beyond Neptune, the comet will resume the state it has known for most of its existence, frozen, silent, moving through a medium so diffuse it is almost indistinguishable from vacuum. The surface will no longer sublimate. The coma will dissipate. The dust will settle. The comet will be inert again, a dark speck against darker space. Only took a few months to pass through the inner solar system. Only took a brief warming to sublimate enough ice to reveal chemistry, to allow measurement, to permit study. And then, back to the cold, back to the silence, back to the billion-year drift through a galaxy that does not notice, through a universe that does not remember. The observations will end, the data will be archived, the models will be updated, and 3i Atlas will continue outward forever, carrying its ice and its history into the dark. A visitor that came and went, leaving only reflected light and spectroscopic signatures, only numbers in databases, only questions that may never be fully answered. There is a stillness that follows departure. The telescopes turn to other targets. The observing programs shift focus. The data is catalogued, archived, available for future analysis but no longer actively accumulating. 3i Atlas recedes beyond detection, beyond measurement, beyond the reach of current instruments. The comet continues, somewhere in the outer solar system, moving at 50-something kilometers per second. It drifts through space too dark and too empty for the concept of motion to have immediate meaning. There are no landmarks, no reference points, only the slow change in distance from a star that grows fainter with each passing year. The ice no longer sublimates. The surface temperature has dropped below the threshold where even carbon dioxide responds to sunlight. The comet is frozen again, locked in the configuration it will maintain for millions of years, until chance brings it near another star, or until it drifts forever without such encounters. Silence is not the right word. Sound does not travel in vacuum, but there is a quality of isolation, of separation, that deepens as the distance grows. The comet moves through a medium where collisions occur perhaps once per century, a hydrogen atom, a dust grain, events too small and too rare to measure. Years pass, decades. The comet crosses invisible boundaries, the orbit of Uranus, the orbit of Neptune, the scattered disk. These are human designations, lines on maps that do not exist in space. The comet notices nothing. It continues. Eventually, the heliopause, the transition from solar wind to interstellar medium, a change in plasma density, in magnetic field strength, in particle flux. But the comet is not equipped to measure these things. It simply moves from one regime to another, crossing a boundary that matters only to those who study such transitions from very far away. Beyond the heliopause, the sun is just another star, bright, but not dominant. One point of light among countless others. The comet's velocity carries it away, increasing the distance by 58 kilometers every second, by 5 billion kilometers every year. In a century, half a light year. In a millennium, 50 light years. The galaxy rotates. Stars move through their own orbits around the galactic center. The sun travels its path. The comet travels a different path, at a different speed, in a slightly different direction. Over time, the separation grows not linearly, but as a function of relative velocities and galactic dynamics. Perhaps, in 10 million years, 3i Atlas will pass near another star. Perhaps it will fall inward, be warmed again, sublimate again, glow briefly in the instruments of some other civilization, or in the view of planets with no civilizations, or in empty space where no one observes. Perhaps it will not encounter another star for 1 billion years. Perhaps it will drift through the Milky Way, participant in the slow churn of stellar populations, affected by the collective gravity of the galaxy, but never again warmed by a single sun. There is no way to know. The trajectory can be calculated for a time, but uncertainties accumulate. Small perturbations from passing stars, from molecular clouds, from the distributed mass of the galaxy. Over millions of years, the path becomes unpredictable. The comet will go where gravity takes it. It will arrive where velocity and time decree, somewhere in the dark, moving, silent, frozen. A visitor that came and went, a traveller that paused briefly in warmth and then returned to cold, a carrier of ice older than the sun, of chemistry from another system, of history written in molecules and dust. The observations have ended. The story continues, unobserved, unrecorded, known only to the universe itself. The comet drifts. The galaxy turns. Time passes in quantities too large for human comprehension, and 3i Atlas, anomalously massive, unusually aligned, chemically distinct, moves through the space between stars, as it has for billions of years, as it will for billions more. Sleep. Rest. Let the comet travel its path. Let the ice remember what we cannot know. Let the dark be dark, and the cold be cold, and the motion be motion, unwitnessed, unmeasured, continuing. The universe is patient, the scales are vast, and somewhere, far beyond where our instruments can see, the visitor keeps moving, carrying its frozen cargo into distances we name but cannot truly imagine, into futures we calculate but will never observe. Rest now. The story has been told as far as telling reaches. What remains is silence, distance, and the slow drift of time itself.